Hey, AUB Physics 210 students, we're in the final stretch now. So in this explainer, we're going to break down two really foundational topics for your final exam. We're talking electromagnetic waves and optical interference. Let's make sure you're totally ready for this. All right, we're going to be focusing on the key ideas from chapters 33 and 35, really getting into exactly what you need to know to nail these concepts. First up, let's get to the heart of it all, the fundamental nature of electromagnetic, or EM, waves. I mean, what is light really? Okay, so at its core, an EM wave is kind of like a dance between two fields in perfect sync. You've got the electric field and the magnetic field. They're both oscillating, but here's the key. They're at right angles to each other, and they're also perpendicular to the direction the wave is actually moving. That whole perpendicular motion thing, that's exactly what makes it a transverse wave. This slide really sums it all up, the four fundamental behaviors of any EM wave. So it all starts with some wiggling charge, an accelerating charge which creates the wave. Then that wave takes off, traveling at the universe's speed limit, c, in a vacuum. And crucially, the electric and magnetic fields, they oscillate perfectly in phase with each other, and together they carry energy in the direction you get from E cross B. And here it is. This is one of the most beautiful results from Maxwell's equations. What's so amazing about this formula is that the speed of light, c, isn't some random number they measured. Nope. It's derived directly from two fundamental constants of the universe, the permeability and permittivity of empty space. It's a universal speed limit, literally baked into the fabric of space-time. You know, the E and B fields, they're not independent. They're totally linked, like two sides of the same coin. Their strengths, or amplitudes, are tied together by the speed of light. And this is super important. The direction that the electric field is oscillating, that's what we define as the wave's polarization. So the big takeaway here is that energy in an EM wave isn't just sitting there, it's moving, it's flowing. The pointing vector, S, is the tool we use to track that flow. It points in the exact direction the energy is going, and it tells us how intense it is. You can think of it as the arrow showing you where the wave is delivering its punch. Okay, so we get how light travels through empty space, but what happens when it actually hits something, like when light goes from the air into a pool of water? Well, this slide shows the two basic things that can happen. Some of the light just bounces right off the surface. That's reflection. And the rule is simple. The angle it comes in at is the angle it leaves at. The rest of the light goes through the surface, and when it does, it bends. We call that refraction, and it's all governed by Snell's law. These two simple ideas are behind everything from mirrors to camera lenses. All right, now for something really cool, one of the most fascinating behaviors of waves. What happens when two light waves actually meet and try to occupy the same spot at the same time? Thing is, these interference patterns don't just happen with any old light. They need a very special condition called coherence. All this means is that the two waves have to have a stable, locked-in phase relationship. You know, they have to be marching to the same beat. And that's why, as you're about to see, many experiments just take a single light source and split it in two. And this is the experiment that proved it all. It's a landmark. By shining a single beam of light through two tiny, super close slits, Thomas Young created two perfectly coherent sources of waves. And when those waves interfered with each other, they created a pattern that was just undeniable proof that light behaves like a wave. So how does this pattern of bright and dark spots actually form? It really all boils down to one thing, the path difference. Just look at the chart. When the difference in the distance traveled by the two waves is a whole number of wavelengths, they show up at the same spot perfectly in sync. They build each other up and bam, you get a bright spot. That's constructive interference. But what if that path difference is off by just a half wavelength? Well, then they arrive totally out of sync. They cancel each other out completely, and you're left with a dark spot. And that, right there, is destructive interference. And hey, this isn't just some old-school experiment from a textbook. The very same principles of interference are behind some incredibly precise instruments, like the Michelson interferometer. We're talking about tools that can measure distances and tiny changes in length, all the way down to the scale of a single wavelength of light. It's amazing stuff. So, as you're gearing up for the final, the most important thing is to see how all these topics connect. Your understanding of basic waves from chapters 16 and 17, that's the foundation. That leads right into understanding EM waves in chapter 33, which you absolutely need to really get what's happening with optical interference in chapter 35. It's like a chain of ideas. Every single link matters.
Look, all your hard work is about to pay off, but don't just memorize the formulas. Try to really visualize what they're telling you. Picture the waves bending, see them adding up and canceling out. Getting that deeper conceptual grasp of what's going on, that's your real key to acing the final.
Good luck with your studies, AUB Physics 210. Seriously. And as you're preparing, just take a second to look around you. Think about the shimmering colors you see on a soap bubble or in an oil slick on the road. How might these fundamental rules of light and waves be shaping the world you see every single day?